So I'm preparing the live stream now. So it should be connected in about. All right, great. So I'm preparing the live stream now. So it should be connected in about. Okay, so the live stream is done. All right, so let's welcome Dr. Banerjee with us. Just a second. Okay, so we have Professor Dipankar Banerjee, who recently appointed as the director of the Aryabhatta Research Institute of Observational Sciences, or ARIES, in Nainital. He is an astrophysicist working in Indian Institute of Astrophysics for past 15 years. He did his bachelors in physics from St. Xavier's College and masters in theoretical physics from University of Kolkata. He has obtained his doctorate from IIA, that is Indian Institute of Astrophysics, and completed 2 postdoctoral tenures in reputed institutes in Europe. Dr. Banerjee's area of interest is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on space weather. He is the head of science working group and co-PI of coronagraph payload to be launched on Indian satellite Aditya by ISRO. Aditya is the first dedicated Indian mission to study the sun, expected to be launched around 2021, that is in coming few months. He is also the project coordinator for the National Large Scale Telescope Project. It is a proposed 2-meter ground-based telescope planned to be installed at a Himalayan site. He is also involved with NASA's Punch mission that is going to launch in next few years. He has peer-reviewed 100 publications with over 1,800 citations in international journals. He is a member of various international scientific organizations like Royal Astronomical Society of the United Kingdom, International Astronomical Union, etc. He actively participates in public outreach programs to popularize science education, traveling to remote corners of the country. And today, Dr. Banerjee is with us live for all of you to learn and understand about the upcoming annular solar eclipse of June 21, 2020. So over to you, Dr. Banerjee.
Thank you. Thank you very much for this opportunity. Now in this difficult time, we have only the opportunity of remotely getting in contact with the younger generation. Ideally, I would love to, meet people face to face and share our excitements about what we do. And the forthcoming eclipse is one such celestial event. During that, one can enjoy these, activities and also learn about, why do we do, study sun and so on. So let me first share the screen and get to the presentation which I have. Let me get into the presentation mode. Oops, no, this is much later. I have to, sorry. I have to go to the first slide. Okay. So are you able to see my slides?
Yes, sir.
Okay. So my plan is I will very briefly try to first tell you where I am now and just briefly introduce our institute in Nainital. So here I am at the top of this Manora peak. Are you able to see my cursor as well?
Yes, sir.
Okay. So we are 10 kilometers south of Nainital city, and we are in top of this hill. And we have another campus called Devasthal, which is 50 kilometers east of Nainital city. And Devasthal hosts the largest, nighttime telescope of Asia now. So these are two exciting national locations where, you're most welcome to visit us and see what exciting things we do. So this is again a bird's eye view of the campus where I am. There are several red boxes you can see. We have many facilities. This is the place where earlier the Udaipur, not Udaipur, the UP State Observatory was. And then later on in early 2000, this was taken over by Department of Science and Technology, and this is now an autonomous institute. So we have, a 40-inch telescope and a solar telescope and other labs and so on. But more recently, we have now moved our major observational facilities to the top of this hill, because this is really a unique site in the country. It is about 2,500 meters above sea level. And we have many new facilities which are identified here. As I mentioned already, this is the 3.6 meter nighttime telescope, one of the largest in this part of the globe, and the largest in India. We are also setting up a 4-meter liquid mirror telescope, and this should have the first light anytime now. In fact, we were already scheduled for this, but because of this difficult time, we couldn't get the experts visiting us last month. This is a 1.3 meter telescope, which is again, you can see the background, very beautiful side, the entire Kumaon mountain range you can see. So apart from doing our work, we also enjoy the nature. This is particularly dedicated for looking at transient objects in the sky, supernova explosions, gamma ray bursts, active galactic nuclei, and so on. Incidentally, just a few hours back, we observed the occultation of Pluto. So this is again, you will probably see a press release very soon. So just last night, there was a occasion. These are the occasion of also these occultation methods. Transit of planets are used for discovery of new planets in other solar system. But this was, of course, in our own planet, which was crossing over a known star, and looking at this star's light curve, what that means, the intensity variation, you can get more information about the Pluto's parameters. So this is just a few hours back. I'm just, what I will try to do during my talk is, I will try to share, the kind of excitements what we go through on a daily basis. So again, I primarily work on sun, but there are many other astrophysical objects in the sky, and my colleagues, how they feel excited on a daily basis. That is the thing which I would like to share with you. So this is the telescope which observed, yesterday night, the Pluto's occultation. I was mentioning about this 4-meter class liquid mirror telescope. This will be again the largest from this part of the globe when it is, all set up. This is a 3.6 meter telescope. You can see the building, beautiful location, and this is particularly suitable for looking at extragalactic sources, distant objects, and so on. This was inaugurated by our Prime Minister a few years back, remotely from Belgium, because this telescope partly was built with a Belgian consortium, and the Belgian Prime Minister and Modi ji jointly inaugurated this remotely. So that's all about, about our campus. These are the 3 big telescopes in Devasthal. So you're most welcome to come. Now let me move to our object, or my closest star. What I work on is the sun. So the sun, what you see on the sky is actually the surface of the sun, which we can normally see. That's called the photosphere of the sun. Inside the star, which is our nearest star, the sun, you can't see. So you, from direct or indirect observations, you get to know about what is there inside. But it is important to know what's happening inside the star, because that dictates the star's atmosphere and so on. So right inside the core of the sun, there is this thermonuclear reaction takes place, and hydrogen gets burned to helium, and a lot of energy is created. So about 30%, which is now shown here, is called the core of the sun. Then energy is propagated through this process called radiation. Energy can be transmitted by different processes. So the radiation is the most prominent mechanism through which the energy is propagated through these layers. And then the last 30% of these layers is called convection, because it's like, you start boiling water. Initially you supply some heat from the bottom, then after a certain time, when the temperature gradient is maintained, then you will see that the the hot material will go up to the surface, and then the cooler material will go down to the surface. So this sets in the convection. So basically, sun is like a convective ball. So of course, sun is also very hot. So it's like a plasma blob in the sky. So when we look at the sun with our visible eye, our eye is sensitive to the visible light, we see the surface of the sun, which is called the photosphere. But when you go to the atmosphere of the sun, then typically what happens? I mean, if you are going away from the Earth's atmosphere, if you go to the hills and so on, the mountains, the temperature is expected to go down. So here what is plotted is in the x-axis you have the temperature, and this is the height. So this is the height of the atmosphere of the sun. So when we go from the surface to the about 500 kilometer, temperature drops, but then very surprisingly the temperature actually increases with height, which is not expected. In a standard thermodynamics, you all guys must have studied the basics of thermodynamics in your schools or colleges. You expect that if you go away from the source of the heat, your temperature will go further down. But here what is happening is the temperature goes higher and higher. So this is a mystery as far as the solar atmosphere is concerned, that how it is that the solar atmosphere hotter than the surface. And because of the atmosphere is much hotter, it actually emits in much, much shorter wavelength. So from ground, when you want to see the atmosphere, you actually cannot see it because it emits into much, X-rays and extreme ultraviolet rays and all that. So if you want to study the atmosphere of the sun, then essentially you have to go to space. From ground-based facilities, you cannot observe the atmosphere of the sun because the hot surface, which is emitting all the emission in the visible light, is too strong. But then there is actually an exception. When eclipses happen, particularly when total solar eclipse happen, then moon blocks this solar disk. So the solar disk, which emits this bright emission in the visible light, is completely blocked. Then the emission from the atmosphere of the sun comes out. As I mentioned, the majority of the emission is actually in the shorter wavelength, but there are also very highly ionized, iron elements and so on, because of the high temperature. The temperature is as is marked here, about 10 to the power 6. It emits some optical radiation also, but that radiation is actually 10 to the power minus 6 times than the visible surface. So when the visible surface is, millions times brighter, you cannot see the atmosphere. But when total solar eclipse happens, then moon, beautifully blocks the solar disk, and then we start seeing the, atmosphere of the sun. That's the outer atmosphere of the sun called the corona. This is a different corona. We are all familiar with a very dangerous corona now. Incidentally, this name of this virus also has come from the picture of the sun. So actually, solar corona during the eclipses, image was very similar to the structure of this virus. In fact, that's the reason why this virus was also called coronavirus. That's actually history. So as I mentioned, that typically inside the sun where the thermonuclear reactions are taking place. So here what is plotted here is, this is the solar interior, and there where the core, the thermonuclear reaction takes place, and then we go to the surface, the temperature drops to 6,000 Kelvin. But when we go again outside, so probably there is a little problem here. This box is actually rotated in the wrong position. I'm sorry about that. This solar interior should be here. It has moved there. The surface is also shifted here. So this is the outer part of the sun. This boxes which is called the corona, and that temperature is millions of Kelvin. And in fact, here what is shown is, this is a solar disk image, but taken from a satellite again. And this outer atmosphere of the sun is recorded by another satellite image. And these two images has been superimposed to give a good overall picture of this. But now what we understand, sun is actually a star, but it is also having lots of magnetic field. And magnetic field, the presence of the magnetic field actually is crucially dictating what is going to happen with the atmosphere, what kind of dynamics, what kind of changes which will happen. Is the sun always there? I mean, emitting the same amount of energy? Actually not. So variations happens in the sun. Sometimes there are variations in the terms of few minutes to few hours, and then there are sometimes changes which happens over time scales of years to hundreds of years. So all these changes, are quite important for our presence and our climate. As you can imagine, we are existing here because of the presence of the sun at an appropriate distance and the solar radiation. If the solar radiation changes, then our existence, our climate, everything will get affected. So it is very important to study the solar atmosphere and its changes and so on and so forth. So here again there is a figure here which is an image of the sun taken from again a extreme ultraviolet filter from a satellite. What you see, there are certain regions where things are very bright. Wherever there are these bright regions, they are called active region, because there are strong presence of magnetic field. And I think you have all studied this bar magnet. And the bar magnet, if you see the lines of force, the field line starts from one polarity and ends into the other polarity. So here exactly what is plotted here is the magnetic lines of force. So wherever these are very strong fields and these field lines are closed, they are called magnetic closed active region. Also, you see there are at other part of the sun, there the brightness is slightly less and there seems to be slightly darker and cooler. And there, what we understand now is the magnetic field is more open. So this is a very important, property of the magnetic field. We need to know what is the location, what are the locations where magnetic fields are, and then what is the connectivity of the magnetic fields of different polarities, because that dictates whether these plasma which is there in those regions will be confined there, or whether they will explore or they will escape from the sun. So all these kind of phenomena are very important in terms of our space weather. So why I'm putting this context of the magnetic field and so on is, historically, see, before the satellite era, we had only the opportunity of knowing about the atmosphere during the total solar eclipses. So total solar eclipses was very important for the study of the sun and its atmosphere and so on. There are major discoveries which has also happened during the eclipses. I will briefly talk about it because I think very nicely in a previous lecture, you heard about the history of the eclipses. I will not go back to that old history, but I will talk about probably last 100 and 150 years where major scientific discoveries were there. So my emphasis will be more on the science part of it, why eclipses are still important. Apart from the, as I mentioned, apart from the, this is a spectacular celestial event, you should observe it. But being a scientist, our motivation is always also to do some science, what is not known yet about the solar atmosphere and so on and so forth, if you could get those informations during the eclipses. So in that context, I am trying to put you these background solar physics as well. So now what we understand is source of the sun's activity is its magnetic field. What is shown here is actually Earth's magnetic field. Earth also has a magnetic field, which is the north-south. And interestingly, the other important element is the rotation axis and the magnetic axis are not actually co-spatial or the same axis. So there is a certain angle between that, and that makes life much more complicated and so on and so forth. So similar thing happens in the sun, but unfortunately in the sun, because sun is much away and so on and so forth, and the solar atmosphere is very thin and we do not have a very regular observations, we do not have a direct observations of these magnetic field in the atmosphere. We have more information available of the magnetic field on the surface of the sun, because as you can imagine, there we have very regular observations and there are strong fields and there are certain effects of the magnetic field on spectral lines called Zeeman effect. If somebody is interested, I can talk about it later. that allows us to measure the magnetic field on the surface of the sun. But in the atmosphere of the sun, how much strong it is and what is the different kind of field lines it is connected and so on and so forth, we do not have a direct observation. So what we do is we make a lot of theoretical modeling. So this is a picture, very nicely you could see this is produced by theoretical calculations. So these are theoretical simulations. Again, I thought I will share some of our daily experiences, that how different kind of physics we try to compare with. Some people do observe, they just look at the different images, they do spectroscopy and so on, and there are certain people, they just do analytical calculations, then they put it in a computer and look at the output from the computer simulations. But the interesting thing is, when you compare the simulations with the observations, then only you get a verification, because no physics is complete unless it is experimentally verified. So you guys are all familiar with the laboratory experiments, but our lab is far away from us. It's all the way there in the sky, in the sun. So what we do is we collect this information from the sun through observation. We run theoretical calculations, and those numerical computer simulation output is compared directly with the observations. And here it is an example. This is the observation. These images are again solar atmospheric emissions of the corona. So if I now compare with this observed images and compare with these numerical models where they are showing how the field lines are collected, they look pretty similar, right? They look quite okay. So our theoretical predictions or theoretical extrapolations are matching pretty well with the real observation. So this is again a very, very interesting aspect what the modern astronomy we do. And again, if you have real, I will talk about some of the observations during the eclipses and how it has been compared with theoretical models, which predicted actually how the corona should look like. So now we understand that this global field is quite an important aspect, because we do not have a direct observations of that. Here I am citing an example of work which is done one of my colleagues in Kolkata. This is ISRO Kolkata. We have a Center for Space Sciences, and there Professor Dipankar Banerjee and his group, they are doing these kind of calculations. They are actually, these are all theoretical predictions, and then you compare. This was the prediction which the SESI group did, and then the next day the eclipse observations were there. So this paper was published only 1 week before the eclipse happening, and then once the eclipse happened, then the people compared, and then of course if you see certain differences and all that, then you go back to your theoretical model and try to refine it, where the problem was, why didn't it match, and so on. So this is an exciting thing from total eclipse one can do. So this is again a comparison between the prediction and reality. So I'm just going back and forth, flipping back and forth. This is a prediction and this is a real observation. So you see the overlap is pretty good. So theoreticians are able to predict how the eclipse should look like, in coming days from their theoretical calculations and so on. So this is a left example was a total eclipse during 2017. The right one is 2nd July 2019, which incidentally I was also witnessing from Argentina. So this is a movie I will play. This
to put
gives
things in perspective, here's
sorry,
the relative size of the...
Let me stop for a while. I hope you'll be able to read this. This is an animation by Jared Owen, and I felt that it's a very nice resource, and I have given the link. You guys can refer to it and understand why there are different type of eclipses, why eclipses are not happening all new moons, because otherwise, you are expected to see, this every new moon you should have an eclipse, but it's not the case. Why it is so, and so on. So this is nicely explained by this animation, and you can refer to that. So please go through this. It's a 3.5 minute kind of animation. It really, really gives you, very good explanation. And then I can explain it further also if there are questions. You please confirm that you're
Hello. So your screen has frozen here. Hello. Hello. Uh, sir. Looks like we have lost Dr. Banerjee or some internet connectivity issues. We'll wait for him to rejoin us and then we'll continue. Please wait. Hello.
Yeah, sorry, you had a breakout in the Zoom session for some reason.
Is that?
Yeah, the Zoom session got broken in between.
Yeah. Anyways, we can continue from the same slide.
All right.
Just
Yeah. Just let me share the screen and you're able to see the. Are you able to see the screen now?
No, sir. I can still see you. Now I can see the screen.
Okay. No, sorry, this is a different presentation. Yeah. Let me.
To put things in perspective, here's the relative size of the sun, the moon, and the earth. The sun is about 400 times bigger than the moon. Now let's look at the actual distances between them. The sun is also about 400 times further from the earth than the moon is. This is why the sun and the moon appear to be about the same size in the sky. So now you know that the animations on screen are not always drawn to scale. The moon's orbit is actually not a perfect circle. It's in the shape of an ellipse. When it's closest to the Earth, we call it perigee. When it's farthest away from the Earth, we call it apogee. It's only a small difference, but it's enough to cause the moon to grow and shrink as seen from the Earth. Okay, now we get into some rare events with the moon. Each time a new moon happens, there's a chance that the moon will block the sunlight and cause a shadow to appear on a portion of the Earth. When this happens, it's called a solar eclipse. The reverse can also happen. Each time we have a full moon, there's a chance that the Earth will block the sunlight from reaching the moon. We call this a lunar eclipse. So now the question is, why don't we get a solar eclipse and a lunar eclipse every month? As the Earth orbits around the sun, we can map out a 2D plane that's referred to as the ecliptic. The moon doesn't orbit on the same plane. It's tilted by about 5 degrees. This means that most of the time, the moon passes above or below the sun as seen from the Earth. We can map out 2 invisible points in space at which the moon's orbit crosses the ecliptic. We call these the lunar nodes. When they line up with the sun, earth, and moon, that's when a solar eclipse or lunar eclipse will occur. This is referred to as an eclipse season. These happen about twice a year. During an eclipse season, there's no guarantee that you'll be able to see anything. In the case of a solar eclipse, the moon may pass slightly above or below the sun and give us a partial solar eclipse. This won't really dim the sunlight enough for us to see it. When the moon entirely crosses the sun, we will be able to see it. If the moon is closer to apogee, then it will appear smaller and we'll get what's called an annular solar eclipse. If the moon is closer to perigee, then it will appear bigger and we'll get what's called a total solar eclipse. Even if you're lucky enough to be on the right spot on the Earth, the longest you'll be able to see a solar eclipse is about 7 minutes. You'll need to be under the umbra, which is the darkest part of the moon's shadow. For a lunar eclipse, the Earth is the one casting the shadow. We may see a partial lunar eclipse or a total lunar eclipse. This can be seen from anywhere on Earth where it's night and will last for several hours. For about an hour, the moon will appear red because of the sunlight bending around the Earth. This is where the term...
Okay, so incidentally, I do not know whether anybody could see this, lunar eclipse the day before yesterday. There was an opportunity there, but it was a little cloudy, so we couldn't see this redness because that depends on the atmosphere, our atmospheric conditions. So I think that animation really nicely explains, why do you get, solar eclipse, total solar eclipse or annular solar eclipse. It also explains the lunar eclipse. Essentially, these three bodies has to be in the same line, and also it has to be in the same plane. So the inclination between these two different orbits makes it, different, and you don't see the eclipses in every new moon. So that is what is explained in this particular diagram as well. So anyway, our slides will be all available. The video will be also available. So I hope this will give you a better clarity when you go back and look at these diagrams. This is pretty straightforward that way. Now I will just go through a little history, not too much, but as I said, Professor Mayank Vaiya has given a very good historical perspective. So Kepler, as was the first to give the scientific description of these eclipses in terms of his orbital motions and all that. What all animations we underwent last few minutes, Kepler nicely explained some of these elements. Then Edmund Halley, who was the famous Halley's Comet, named after, predicted the timing and path of the total solar eclipse on May 3rd, 1715. I think from your earlier presentation with Dr. Vaiya, he has given you, some insight that how this eclipse timing, predictions were, taken very seriously by ancient civilizations almost, and some of the king and lords, they really, meditated a lot of people who could predict it well, but then punished also some people who couldn't predict it, correctly. So Halley's calculations were only 4 minutes and about 30 kilometers off from the actual timing and the path of the eclipse. So you can see it was not easy to make these calculations so accurately because of, they still didn't have the, accurate, numbers in terms of the different orbital distances and so on. These are again historical first few photographs. If you can take any of these photographs in the near future, when such eclipses happen, that you will be feeling very excited. I can guarantee that. During the eclipses, the first few seconds of the totality, you get a very beautiful, sight. These are called Bailey's beads. This was again discovered around 1836. They are caused by the moon's mountains, valleys, and craters. So on the surface of the moon, if there are some gaps, basically light comes through those gaps, and then you see this, beautiful Bailey's beads. This surface features creates an uneven edge of the moon, where small beads of sunlight still shine through the lowest part for a few moments after the rest of the sun is covered. So essentially, first, few seconds of during the second contact and also the third contact, you can see this Baily's beads. Multiple images taken in quick succession show the beads disappear and appear in stages with only a very few deepest valley and craters allowing the sunlight to shine through the closest of them. So these are again historical pictures which you can refer to. Then scientifically, this was one of the major discovery during the eclipses. And in fact, people in the terrestrial labs were not aware of the element helium. And during the total eclipse, Pierre J. Jensen in 1868, he traveled to India. In fact, he traveled to a place in south of India near Salem, now in Guntur, actually it's in Andhra Pradesh, and he measured the solar spectrum during a total eclipse and observed a new yellow line which indicated a new element. So people didn't know what was this element responsible for this new yellow line. And then Joseph Norman Lockyer recorded the same line by observing the sun through London smog. So again, these are historical almost evidences, as I was trying to tell you, that you observe, astrophysical objects, you observe certain things in their local terrestrial environment or in the lab or in the computer, and then you compare your, observations to, get into a discovery. So that's the, historical, again, another story that this new element was considered to be, of course, it was initially not named, but then it was later on named by helium. And in Greek, in Latin, actually, the word sun is helios. Since it was first observed in the sun, so it was named as a helium. Then this was actually a so-called, at that point, I thought to be a discovery, but later on it was found out to be a mistake. So there was a fake element was named called coronium. Charles Augustus Young and William Harkness in 1869 separately observed a line in the green portion of the solar spectrum that didn't correspond to that of any known element. Again, if you see certain line in the overall spectrum, you try to go back to your atomic spectroscopy knowledge, and then I can identify what particular element is responsible for that line. So that is how spectroscopy is done for all astrophysics, astrophysical objects as well. But then it was named as coronium, but later on in 1930s, Young and Harkness found out that it was not a new element, but essentially it was a very highly ionized iron line. So what happens is, as I mentioned before also, the outer atmosphere of the sun, which is called the corona, here you see the picture of the corona, is very hot. It tends to about 6. So when you take an element and provide sufficient energy, a lot of outer electrons gets knocked off from the outer orbit, and then you get ionized element. So this was due to a very highly ionized, iron line, which people observed during the eclipses. So we regularly observe those iron lines, and we take images of those iron lines during total eclipses. I have done such experiments as well. Then again, there was a chasing a non-existing planet called Vulcan. So Maria Mitchell and James Craig Watson and Thomas Edison set out to take advantage of this 1879. So these 2-year eclipses were very, very important historically to catch a glimpse of this planet called Vulcan. So never before observed planet that scientists thought was causing Mercury's irregular orbit around the sun, but it turned out to be later on was a mistake, because people were not aware of the Einstein's general theory of relativity, which were published much later in 1915, and that explains the Mercury's unusual path. So it was not a new planet, but it was just a new positions of the Mercury. Of course, the validation of general theory of relativity was done. This was an expedition led by Eddington, the British scientist, and in May 29, 1919, it was a famous discovery of general verification of the Einstein's general theory of relativity during eclipses. So total solar eclipses really provided big opportunity in the past. Of course, now we have possibilities of going to space and create artificial eclipses. There are instruments called coronagraph that artificially blocks the solar disk, and we observe the solar, corona as and when we want. So the importance of the total solar eclipses have slightly reduced, but again, there are certain limitations of the kind of experiments you can do from a space platform because of the limitation of size, the limitation of data, what you can collect and download it and so on. So even today, if you want to run a very new experiment which needs heavy equipment and more modern sort of cameras and so on and so forth, then you still look for the opportunity of the eclipses and set out your experiments. So during eclipses, possibilities are precise determination of the shape of the moon, as you can see from those images, and the timing information. A lot of these things can be done, even in terms of the moon's valley, where those craters are and the hills are. So those kind of models are there, and those things can be verified during the eclipses. But just looking at the location of the Bailey's beads and the diamond ring and so on. So it also allows you to measure accurately the diameter of the sun, because as you can imagine that these two objects, the relative sizes of these two objects has to be perfect to block one another. Although, as you can see from this animation, sun is much bigger but much away. But because the relative distances are different, they appear to be of the same size during the total solar eclipse. And when that happens perfectly, then only you get the total solar eclipse. Otherwise, you get the annular solar eclipse, as it was explained in the animation as well. There are also geophysicists, those who work on Earth's atmosphere. There are certain effects during the eclipses people study. People also study effects of of eclipses on animals or plants. There are certain effects of on the shadows. So there are quite a few experiments one can do during the total eclipses. So as again you have seen that typically there are 3 solar eclipses. I'm only talking about solar eclipses today. Annular, when the two sizes do not match exactly, you see annular eclipses. Of course, when it matches perfectly, you see beautiful total solar eclipse. I must admit, total solar eclipse is a different thing altogether. And I mean, I have seen some 7 total solar eclipses from different parts of the globe, and it's fascinating. I mean, it's still I can't get sleep when such thing comes. And of course, partial eclipse is more of a celestial phenomena. It is not as spectacular, visually, I would say, because when total eclipses happens, everything suddenly changes. I mean, in the midday, you see that temperature drops, the birds start getting confused, they go back to their nest because thinking that it's evening. So I mean, the entire nature gets a little confused, and suddenly you see stars in the sky in the middle of the day, or in the early morning, depending on the totality durations and so on. So that's actually a different ball game altogether. So partial eclipses, different phases. Of course, you see on the sun also there is some dark, dirts on the on the surface of these images. They are called sunspots. And as I mentioned earlier, those bright locations on the UV images from the satellite, which I showed you earlier, are these sunspots. So these are again very strong magnetic field concentrations, and they play a major role in controlling the atmosphere of the sun. So this is annular eclipse, different phases. And as you can see, you expect this to see in coming weeks now. And the preparation has to be for that. This is total eclipse, different sequences. And as you can imagine from the partial thing, of course, this is a diamond ring in the second contact. And then you have the possibility of seeing again the diamond ring in the third contact. Depending on again where the moon's valley will be, you'll be able to see this. I will share some of my experiences, recent experiences on total solar eclipse. My first experience was when I was very young in schools from Diamond Harbour, Kolkata. I don't remember too much. It was spectacular. This was way back in 1980. But then when I was doing my PhD, I was selected for a air experiment from a AN-32 Russian aircraft. So we flew out of Agra. I have not included my pictures here, but that was a spectacular total solar eclipse seen from different parts of India, and maybe some of you have seen that. Then in '99, I was in Irish Sea, so I was in a with a sea cruise ship, and we saw the eclipses from the cruise ship. But more recently, I started doing more scientific experiments. So this is a eclipse where we went to China in 2009, and you can see that we had lots of equipment, almost a ton what the equipment was transported. We had two telescopes here. You can see where we took images during the totality. So this is the images. This is again an iron line image. This is not a white light corona what you see, but there are specific experiments which we did. So this was the team. Of course, I was much younger, if you can identify still. Then this is again the same experiment. There were spectrograph channels, so I will not talk about too much details about these experiments, but if somebody is interested, I can share. We had major scientific publications in referred journals, 2 or 3 in that time. Then the following year, I was again very lucky to be part of a eclipse expedition to Easter Island. This is middle of nowhere, actually. This is a small little island which takes again 4 hours to fly from the coast of Chile, and I was fortunate to be part of that expedition. And this was the totality, and as you can see, this totality is all in the water body. I mean, there were no actually almost no land mass where this totality was visible. So either possibility was you are in the ship, but from the ship you cannot run stable experiment. So you look for small little island. So we identified this island called Easter Island. It has its own historical significance of these statues. They're world famous, and a lot of mystery is there. How these civilizations were there several thousand years before Christ. So it's very exciting. This is the island, very small island, and we were at the coast somewhere. And these are the statues. You see the island. This was the team. We had, these are called celostats, that, you get the image onto these kind of mirrors, and then the reflected light goes into that, and then you take that beam back into your tent, because you run the experiments inside the tent there. So even our Indian ambassador came from Chile to participate with us, and we shared our experience. This was more recent. This is 2nd July 2019. I was not in this particular location. This is an animation from Chile, but this mountain range, and the other side of the mountain range is Argentina, and I was in that mountain top. We had a scientific conference, and then we are again privileged to be able to travel to these locations and see these kind of eclipses. So there again, these are very, very exciting lifetime experience. Let us come to our current eclipse, 21st June 2020. This is going to be an annular solar eclipse. So as you can see, the path of totality here, and then a substantial portion on the northern part of India, it is there. And so this is again a map from NASA's website. And you have little TSFC gives you an animation of this shadow, because essentially the shadow tells you where you will see the eclipse. But then again, there is a small little dot, and within the shadow, that essentially tells you where you will find 100% annularity. Other places you will only see the partial phases. This is a snapshot. So in fact, I'm sure most of the people are familiar with this website. I will do some interactive things here. But if you suppose if you are in, so here you see this dark pink patch, that is the total annularity, and it goes through Kurukshetra, Shirsha. I understand, the team will be going to Saharanpur. You are going to Saharanpur, right?
No, sir.
Somewhere.
Srinagar.
Okay.
I'm going
So
to
you'll be
Srinagar.
on the. Okay. Okay. So you'll be on the complete annularity path.
Right. It's in
So it,
Rajasthan.
all right. Okay. 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 Yeah. So unfortunately, I am not able to travel this time. We are closer to Haldwani here, so we will have about 95%. And similarly, in Delhi, this is a snapshot of Delhi. Delhi, the start time is shown. It will have about 93.77%. This is how it will look like from Delhi. So this is the animation that if you are in Delhi, this is the best you will be able to see. So I will go to this time and data website, and then if I just you can do this thing to find out where it is. I just open this link with my browser, and if I just click on any of this location, then you will find this is a location in Uttarakhand where it is 98.16% coverage of the sun. So you will see the start time, you can see the maximum time. This is, you can see it's in midday. So essentially about 12 o'clock. And also it does give you some indication about the weather conditions and so on. So just, feel free to, you can zoom it further and identify your location and, get a better, output from here. So this is in the Tibetan region. Here it's slightly later, and you will see 98%. So you can just play around this with this interactive map. I'm sure majority of you have access to this map or already have seen this. So this will give you a overview where you can expect to see how much of annularity, the start time of the eclipse, the end time of the eclipse, and so on. So please refer to this website. If I could go back to slide. So warning, never look directly at the sun. So this is important. If you can manage to get a eclipse glasses, please use that. But careful, because some eclipse glasses are not really very well licensed, because effectively, you have to cut down the intensity of the solar light substantially by many orders of magnitude. So if you can't do that, it will harm your eye. And if you have a very cloudy sky, sometimes that may provide you a filter, and we'll be able to see the partial thing with caution. But this is the best way of looking at the sun. You can just create a small little pinhole, and then you just look at the image on a white paper or a board or something. So we will have all these arrangements actually from our observatory. So in the observatory, we are not going to see more than 96%. So we'll have a live telecast from this place, and we'll also have some live commentary. If people have questions and so on and so forth, we'll open up a Zoom session and Facebook Live and YouTube Live and so on. All kinds of whatever things are available at that time. And we'll have 3-4 telescopes. We also have a reasonably big size solar telescope with a full disk image in the H-alpha, which gives you a slightly higher atmospheric image of the sun. But it's a nice high resolution image. So there are just a few facts. On average, it takes about 375 years for a total solar eclipse to happen again at a specific location. So if you happen to be in your lifetime be able to see an eclipse, don't miss the opportunity. And even if your neighborhood, a few hundred kilometers of travel, you should take that effort. Unfortunately, now the conditions are not very favorable, so I cannot advise you to do this. So you have to be careful on your, local conditions and so on. But please keep this in mind, for future eclipses and so on. But even if this annular eclipse is possible to be seen closer to your place, don't miss the opportunity. It's fantastic. It's a lifetime experience. Next eclipses. This is the one June we are talking about. Of course, there is a total eclipse again from South America. Earlier, I had a plan to go, but it doesn't look like now this year how things will be, because again, it's in December 14th. Things may or may not, be favorable for long distance travel. But this is again a very good long duration total eclipse. This again list of annular and total eclipses. You can refer to many websites in NASA, SPNA, time data. So just note down those eclipse, where it is, in case you're not able to do it this time. But of course, you can still participate through live telecast. I think many people will be doing that, including your Astro Club here. And we look forward. Hopefully, weather will be good for us to look at the eclipse. So that's more or less what I wanted to share with you guys.
All right. Great. Thank you very much for the lovely and informative talk. If you could just switch from screen share to your video feed.
Sure.
Great. So, thank you very much. It was very, very informative, and I'm sure a lot of the students and interested amateurs would have learned a lot about the sun, especially the content in the beginning about how how you study the sun, the basic physics, right from the heat transfer, energy transfer, and all. So that's wonderful. I have a few participants who have raised certain questions, so that I'm going to speak
Okay.
up here, and you can answer.
So you will read me out those questions, because in the chat box, normally in the Zoom sessions, we try to do that, but probably you are getting the things from your YouTube channel.
Right, sir.
Okay.
So Uttal wants to know, can you explain the mechanism why temperature increases in above the sun?
Okay, very good question. And this is one of the outstanding problems where I have been working for the last 20 years. And so there is a combination of mechanisms which we understand. So since the question has come, I will try to explain it, with few minutes. So what happens is, on the surface of the sun, as I said, the sun is convective. There are a lot of perturbation. So basically, because of these disturbances, on the surface, you can generate lots of waves. So these waves can carry substantial amount of energy from the lower atmosphere to the higher atmosphere. Now, the question is, there are three parts of the question: that how do you generate these waves, how you transmit these waves to higher atmosphere, and then how you dissipate these waves. Unless you damp or dissipate these waves, you cannot transfer the energy from the wave to the local media. So this is now been understood that there are different types of waves also can be present. It's just not sound wave. Typically in a atmosphere, when you create a small little pressure perturbation, you get a sound wave. But since in the solar atmosphere there are lots of magnetic field, so there are a lot of magnetic waves, and these magnetic waves can carry a lot of energy. And there are quite a few mechanisms now we understand which are responsible for damping these waves into the local plasma in the higher atmosphere, namely in the corona, and that provides some energy. But then again, the waves are not sufficient to hit the corona entirely. There is another mechanism which is called magnetic reconnection, which is now invoked for this heating mechanism. Essentially what happens is, when you have two magnetic field lines, so typically the two magnetic field lines, they don't like to talk to each other. They will repel each other. That's a property of a magnetic field. But if you somehow can force them to come to each other, then this magnetic energy gets converted into heat. And it can also accelerate particles which are confined in those regions and so on and so forth. So the magnetic reconnection process now is understood to be a very important process which supplies this heat energy, because a lot of magnetic energy is already available because of the presence of the magnetic field that gets converted into heat, and that maintains a high temperature in the corona. So this is there are also very dynamic explosions happens in the solar atmosphere. I didn't talk about it at all today. They're called solar flares. So flares are nothing but manifestations of these magnetic reconnection process. So there are many flares. There are big flares, there are medium-sized flares, there are small flares. So all these different sizes of flares, they contribute to this energy which supplies the and maintains the temperature in the corona. So that's these are the two mechanisms which are now believed to be responsible for maintaining the high temperature in the atmosphere.
Thank you for the answer. Next question is by Sovan. He wants to know, what is geomagnetic storm?
Okay. So what happens is, as I only talked about flares, so flares are these huge explosions in the atmosphere. When a flare happens, then the amount of material which is confined in those magnetic big structures, they are expelled into the interplanetary space. So these are called coronal mass ejections. So when you have such large volume of plasma material with the magnetic field and charged particles and so on, they travel all the way from sun to earth. Fortunately, earth has its own magnetic field also, and that actually protects us from these big plasma blobs which comes. So these CMEs, when they try to penetrate to our atmosphere, earth's magnetic field interacts with that. So if the magnetic field of the impinging coronal mass ejection and the earth's magnetic field, they interact, then you get a geomagnetic disturbance. So our earth's magnetic field momentarily gets changed in those local areas and so on and so forth, and it creates a lot of electrical disturbances and all that. And so these things are called geomagnetic storms. So because they're related with earth's magnetic field, but the source is actually the sun. These coronal mass ejections which are coming from the sun, they interact with earth's magnetic field lines and result into these storms. And those storms can actually affect our communication systems. It can also affect our transformers. You can get power outages. And of course, if you have a satellite which is in the vicinity of that, that can get damaged. So there are a lot of effects actually which needs to be studied. So this is a very important area called space weather. In the space, how the weather is going to be for say satellite launch, or a very high plane plane you want to travel from India to US, but rather than going through Europe, you take a polar route. And when you take a polar route, these kind of highly energetic particles which are coming from the sun, they try to actually penetrate through the Earth's polar region, and they can actually interact with these of these aircraft as well. So they could be quite dangerous. So the geomagnetic storms are quite an important thing for studying our local environmental effects, telecommunications, and so on.
And the northern and southern lights are also kind of.
So northern lights comes because of this exact phenomena. When these energetic particles, they tend to penetrate through the polar region, because the polar region of Earth has open field. So in the equatorial region, or wherever we are, these energetic particles cannot penetrate, cannot cross the Earth's magnetic field. So they guide about the Earth's magnetic field and then try to enter through the polar region. So that's how we get the northern lights and auroras and so on.
Ruma had a question. I think you have covered this question already, but I'll just speak out. What is sun's magnetic field?
Yeah. So essentially, because the sun is a hot plasma blob, and inside the sun, now we understand the things are convective. There is another big element which I did not talk about today, is sun is also rotating about its own axis. Most of the objects in the sky actually rotates, around its own axis. So sun is no different, but sun doesn't rotate as a uniform, solid body. It rotates actually differentially. The equator rotates much faster than the poles. So this is a very, very, very peculiar and difficult thing to happen for a plasma blob. And sun is not exactly sphere as well. So all these effects generates magnetic field inside the sun. And those magnetic field which is generated inside the sun, they pop up into the surface and form these sunspots. So sun, for that matter, most of the rotating stars, and sun is a sort of normal main sequence star, has magnetic properties as well. So it's a magnetic star that way because of the combination of rotation and convection. So these two yields to the magnetic property of a star.
Okay, thank you. Pradeep wants to know, is the Earth's magnetic pole strength decreasing with the impact of sun's flare?
It does have a very marginal, decline depending on how strong these CMEs are, but it doesn't affect globally. It only affects it, like if you have a magnetometer which measures the Earth's magnetic field at that particular location, it will detect certain change in the magnetic field property. But it will bounce back because Earth has a huge. I mean, you can imagine probably Earth has a huge bar magnet somewhere inside deep interior, so that restores it very, very quickly. So in a local region, you will find some change in the magnetic field of the Earth, but that's very, very locally happens wherever these interactions are.
He also wants to know what will be the main strategy as well as main aspects for collecting data on 21st June annular solar eclipse.
Okay. So I must admit, I mean, this annular solar eclipses, for a high-level scientific, experiment is not more suitable, because unless the solar light is completely, I mean, solar disk is completely blocked, we can't see the solar atmosphere. What we are seeing is actually a rim. So the rim structure is not allowing us to study any atmosphere of the sun. What it allows us to study is the sizes, and because based on the already known orbital parameters and the inclinations, as you saw from the animations and all that, we have precise information about where the first contact will be, where the second contact will be, and so on. So if you have a much more precise clock, those precisions can be improved. But already the knowledge is pretty well developed in terms of the diameter, but it's a good exercise to find out what is the diameter of the sun, what is the diameter of the of moon, and why this percentage calculation, whatever is predicted and what you observe, whether how close they are. So if you have a very precise instruments to measure these timing and the sizes, then you can verify some of the already known knowledge and can improve it further as well.
Uh, Janvi wants to ask, how was angle of inclination of lunar orbit estimated from Earth with so much accuracy?
Yeah. So again, as you can imagine, so in a three-body problem, you go back to all the eclipses observed, all the eclipses, their first contact time, second contact time, and so on, and then you refine your. So in a way, that's how many eclipse observations and all that helps in refining those parameters. So since we have several hundreds of years of data now, so and every year there is at least 2 eclipses. So people have really refined this. So the plane and their their inclinations and so on. It's a very good question, but that's how we improve. So repeated experiments always refine your understanding as well. I mean, you can't make a breakthrough now, but probably it improves your knowledge all the time with new sets of observational data.
Aradhya Jain wants to ask, is it okay to look at the sun through a pinhole camera attached to a telescope?
No, you should never look at the sun through a telescope in any case. Because the telescope again, where the optics is converging the light in the focal plane, your eye should not be there in the focal plane, and you can be completely blinded if you use a telescope. In fact, it's even more dangerous than looking through a naked eye, because naked eye, it's only the atmosphere it is there, but the telescope, it is converging beam. So you should never do that. So the pinhole camera, actually, what I'm was indicating, you are seeing actually a projected light. You are not directly looking at it. So even if you use a telescope also, there also either you take that output to a computer through a camera, or you put a white sheet of paper, and that the image of the sun will be formed on that white paper, and you'll be able to see that. Never look at the sun through a telescope at all. I mean, this is more than dangerous than looking at through naked eye.
So would you recommend using a solar filter also?
So again, so the solar filters, if they're very professionally made, because they are called neutral density filter, so the solar filters, if they are able to reduce the intensity of the light by few orders of magnitude, then it is okay. Even in the past, people used to use X-ray films and all that, but that's a problem, because the emulsion in the X-ray plate also is not sometimes uniform. So you are thinking that, if the film le liya to, and then you look at it, but if the coating of the film is not uniform, certain places, or if there is a small little hole which you are not able to actually identify normally, that's pretty dangerous. So even the sunglasses, what is commercially available, you should be very careful to look at there is no hole or anything in that. That could be dangerous.
Yeah, the simplest way is to look at any bright source of light just to check for any leakage.
That's true. That's true.
Of course, you
That's true.
can't check the uniformity, but at least the holes, even how small it may
No,
be, it's
yes,
visible.
yes, you're right. You're right. Yeah.
Okay. Um, okay. Ashish Kumar wants to ask, how did scientists confirm the relativity theory from solar eclipses?
Okay. So essentially, any gravitating object bends the light which is coming from a distant source, because it's an effect of a strong gravitating object. So normal circumstances, a star which is behind the sun, you cannot see it, right? Because the sun will block that and so on. But because of the presence of the sun, that light which was supposed to go somewhere else, it gets bent because of the presence of the of the sun, and it will appear that it is there somewhere behind on a different location, not exactly where the real location is. You will have a virtual location, because your eye will imagine that the sun that starlight is coming in a straight line. So your thing will be looking at a distant object in the sky. So now this particular effect is also used as a lensing. There are a lot of extragalactic sources are being identified by called lensing. The different gravitating object acts as a lens for converging this. So during the eclipse, that is what happened. And during the eclipse, of course, these stars were visible in the sky, and from those images post eclipse, they identified which star were what locations and so on. And so the bending of the light of that particular star was confirmed.
Another question is, why is the density of sun in pole higher as compared to equatorial position of the sun?
Say it again. The density of the sun.
The density of sun in pole is higher as compared to equatorial position. Why?
Yeah, it's not the density. Essentially, it's a rotation speed is different, because again, you have to think about that sun is not a rigid body. Okay, if sun would have been a rigid body, then again, you have this, density differences and so on and so forth. Because of the rotation, where the rotation speed of the equator is much faster than the pole, then there are certain differences in the internal properties also. So it's an effect of the differential rotation of the sun. So we really cannot comment that the density at particular location is higher or lower based on this.
Utkal wants to ask another question. He want to know, it takes a photon to travel a lot of time to travel from the sun's surface to atmosphere. Is it only due to solar gravity or something else involved?
No, actually, what it takes is the photon to travel from interior to the surface. It takes a lot of time because of high density inside, inside the sun or any star. Essentially, the radiative zone, these photons undergo collisions with another, photon. So this is a process called random walk, and it takes millions of years for that photon to eventually escape from the surface. But once the photon is, escaping from the surface of the sun, it takes its usual time for, propagation. There's not much, difference because the density in the atmosphere of the sun is very, very small, much, much smaller. So that question is actually more valid for the interior of the sun, not in the atmosphere of the sun.
Another very interesting question. Is our solar system tilted around the galaxy?
Yes, there is. We are, as you know, our galaxy is a spiral galaxy. And then we are in one of the arms of that, of that galaxy. So there are different spiral arms, and we are situated much away from the center of our galaxy in so-called Orion arm. So there is always some angle between, different references. So this is what, makes things more interesting in the 3D space. We all look at 2D space when we look at an image on a book or a paper, but in reality, it is in 3D space. And in astronomy, it is even more interesting because it is a 4D space, because there is also a time domain. And the farther the object, the light is coming from, much early time and so on. So this is quite fascinating. Yeah.
All right. So I think these are all the questions. Now I have a personal question I want to know about. Since the eclipse has such a high magnitude, that is very near to total eclipse magnitude,
Mm-hmm.
0.993.
Mm-hmm.
Uh, would you recommend taking out the filter to take pictures during annularity, or should I keep the filters on?
Yeah, it will depend, slightly depend on the weather conditions, because during this typical, cloudy June weather, you may have some clouds, which will already provide you some, reduction in the intensity. So, and again, it will also depend on your camera. How shorter exposure you are able to give. If you have a very good CMOS camera with a very short 1 or 2 millisecond exposure time, then removing the filter, you should be able to get a good picture. Yeah, so you can play around it. And the other thing, what people does these days is they take exposures with with many different exposure times.
Practically.
So that you can then choose it later on. I'm sure you are all aware of that.
I am a little skeptical about removing the filter. If the focal length is high, or if the sun is not well covered, it is going to burn the sensor, and I'll
Yeah.
lose
It's always
valuable time.
dangerous to do that. Always dangerous to do that. Yeah.
Yeah, yeah.
So if it is very overcast or something, you can think about it. Otherwise, I think for annular eclipse, no. But total eclipse, of course, you have to. So
Total eclipses, yes, but because it is such a deep eclipse, I
that's
am
true.
still
But
puzzled.
even what happens is that's a problem with even during the totality. After the diamond ring, it is still dangerous. So diamond ring also you have to capture, with the filter only.
Yeah,
Uh,
yeah,
so
I tried that with 2017 eclipse.
right.
Yes.
So, the diamond ring is only very few percent, right? I mean, also not in the entire rim. It's only in one location. So even then, it's quite bright.
All right.
So my opinion, if it depends on cloudy conditions, maybe you will get a sense of it when you're taking exposures during the partial phases. You may get a better sense of it.
Okay, one question just popped up. Why the number of sunspots are higher in the equatorial region than the polar region?
Oh, very good question. So this guy knows a bit of sun. Okay, so
Ray. He
what's
shares
the name?
your Dipankar Ray. He shares your first
Okay,
name.
I see. Okay, yeah. Ask him to contact the other Dipankar later on for even longer session for that, because this session I can go on explaining for half an hour. Okay, let me not do it, but let me try to do it in a minute. So essentially, the sunspots now, they are formed somewhere interior in the sun. Now we understand that they are formed in the base of the convection zone. I mentioned that the sun is convective inside, and about 30% in the depth the sunspots are formed, and they slowly come up to the surface. But because of this differential rotation, again, the sunspots, they cannot come up to the very high latitude. They are dragged into the lower latitude because sun is rotating faster in the equator. So whenever sunspot comes, we only see sunspots up to 35-degree or 40-degree latitude. We never find sunspots to very high latitude. And again, this appearance of the sunspot in the 35-degree, 40-degree latitude also, it changes with time. So there is something called a solar cycle with 11 years. So sometimes we see more number of sunspots, which is called the solar maxima, and sometimes it is called the solar minima. That means, the number of sunspots on a day will be very few, if not any. Sometimes, there are months over which you won't find any sunspot. So again, coming back to this, his question, because of the differential rotation of the sun, the sunspots, when they pop up into the surface of the sun, they tend to appear only at 35-degree, 40-degree latitude. Again, depending on the solar phase, they can be also much, much lower. So as he pointed out, during the solar minima, you will find sunspots only very, very close to the equator, not even to 35-degree, 40-degree. But since he asked the question, just to make life a little more interesting, there are stars where the star spots are much stronger than the sunspots. Sunspots are typically kilogauss strength. If you have a sunspot, think about a megagauss strength, then that can come to very high latitude. So there are other stars where do we find, star spots to higher latitudes as well.
Great. So thank you very much for the precious time you shared with us and enlightened us all about the sun and the interesting features about the upcoming eclipse, and also sharing your past experiences with various eclipses you have traveled for. It's certainly very interesting and worth noting that uh, you can travel to exotic places with good reasons other than just holidaying, and that's
That's true.
also very fulfilling and refreshing.
We are privileged. I say, sometimes we have we have a possibility of sort of being able to get our hobbies into our profession. So
Right, right. Great. So, thank you very much, and we will definitely get back to you with more interesting topics where you can shed some light. And I hope you will find some time again for us in the future. And all the best with the eclipse on 21st. We wish you clear skies. Even though 96%, it's worth looking
what
at
what
it.
what the try?
Yeah,
Yes.
great. So,
Thank you
thank
very
you.
much. It has been a pleasure for me, and I hope also you and your team's success in the ensuring Eclipse expedition and the ones which are there in near future. And keep me busy. I have no problem in getting the opportunity to share my experience and knowledge.
Great, great. Thank you.
Thank you.
So next week we are going to talk about how to photograph the eclipse, and we will have Mr. Ajay Talwar, world-renowned astrophotographer, eclipse chaser. He's going to talk about how to photograph the eclipse using very simple equipment. You don't need fancy telescope. If you don't have one, don't get disappointed. We're still going to talk about how to just photograph the eclipse in order to capture the beauty of it. What are the precautions you have to take? And you can keep your questions ready. The next session will be on 14th of this month, 14th June at 3 p.m. And we will send a reminder with the channel link to you again. So thank you very much.
Thank you very much. Okay. Bye bye.